Hello everyone and welcome back to yet another session of Target JEE Advanced brought to you by the team here at BYJU'S. Well, today we are going to look at the last chapter of calculus, which is differential equations. Well, we've spent a lot of time looking at calculus, and we know that calculus is a very important section from the examination point of view. We've looked at limits, continuity, differentiability, methods of differentiation, application of derivatives, and then we looked at definite, indefinite integrals and area under curve. And all of these put together, bulk of your question paper is from here. But do not forget differential equations, because this chapter too fetches questions every year. So how many questions come from differential equations will be discussed in this particular session, and then we will look at some very interesting questions to keep you engaged and to give you a feel of how beautiful this chapter on differential equations is. So first of all, let's look at the JEE Main Examination. Well, the JEE Main Examination is very predictable when it comes to differential equations, because every year, last 5-6 years, we've seen one question has appeared from differential equation, one and not more than one. In every paper or every session, we'll have one question from differential equations. Well, these questions tend to be from the simpler part of differential equations for your JEE Advanced and the main examination preparation, because these questions tend to be from topics such as homogeneous differential equation, linear differential equations. So in general, in the main examination, you have to solve a differential equation. It can be a linear or a homogeneous, or sometimes just the concept of a simple variable separable might be enough to solve this question in the main examination. But the advanced examination is a little bit trickier. Well, that's of course expected, isn't it? Because we can never expect the advanced examination to be exactly like the main examination. It's advanced for a reason. Well, in the advanced examination, some years there have been more than one question, but every year in the past 6 years, there's been one question definitely from differential equations. Well, the years when there were two questions were in fact the years 2015 and 2016. Well, these were the years when there were two different questions which came from differential equations. In 2013, we actually had a multiple correct answer type of question, and this question was not a very simple question. This question involved you to identify patterns in differential equations. Well, this was not a straightforward homogeneous or a linear differential equation type of question. You had to identify patterns and convert the right hand side and the left hand side into specific differentials, and then you had to integrate and arrive at the solution. A tricky question was asked in 2013. Well, 2014 we actually had one single correct answer type of question, and this question was a rather simpler question, and it was from linear differential equations. 2015 and 16, there were two questions. 15 had both of them as multiple correct answer type of questions, and both these questions were tricky questions which involved you to understand the patterns in differential equations and understand the concepts of derivatives, the product rule, the chain rule, and the quotient rule, and use it wisely in identifying patterns in differential equations. Well, these were the questions in 2015. 2016 was again no different. It was again a pattern-based differential equation questions where you had to identify patterns in differential equations based on the different rules in methods of derivatives. So again, two questions this year, both of them multiple correct answer type of questions. But the number of questions have reduced in the past 2 years. 2017 and 18 have seen just one question each. 2017, it was a single correct answer type of question, and this question was based on the variable separable method. But the question was not a very easy one. You had to do a lot of manipulations to arrive at the variable separable form of the differential equation and then solve the question. 2018 too was a variable separable type of question, and this time it was an integer type of question, rather an unimpressive question in my opinion. Based on the last 6 years, this was the easiest of the 6 questions that I've actually seen, but still differential equation can be tricky. So the vital piece of information that you need to keep in your mind when you think about differential equation is the fact that for the advanced examination, the key point is pattern-based questions and differential equations. Looking at the left-hand side and the right-hand side, looking at certain terms, you should be actually able to visualize patterns. And visualizing patterns don't come easy. They come with lots of practice, and that is why it is important that you solve lots and lots and different types of visualization questions and differential equations. For your board examination preparation, you would have solved a lot of homogeneous and linear differential equation questions. So you can actually focus a little less on these and focus a little more on pattern-based questions for the advanced examination. I'm going to quickly solve a few questions by focusing a lot on pattern-based differential equation questions rather than linear and homogeneous and variable separable form of differential equations. So here are the questions, and this is the first one. So in this question, we've been given a function f, and this function has been said to be a non-negative function which is defined in the domain 0 to pi by 2. Further, we've been given two pieces of information. The first one being integral 0 to x f dash of t minus sine 2t dt equal to integral from x to 0 of f of t tan t dt. The second piece of information says that f of 0 equal to 1. Now this is a multiple correct answer type of question, so we have to check which of the four given options are correct. So the first two options speak about f of 0 equal to 1 being the maximum value of f and the minimum value of f respectively. The third option speaks about integral 0 to pi by 2 y dx, and the value of that they say is equal to 3 minus pi by 2. And finally, in the fourth option, f of pi by 3 is said to be equal to 1. So we have to check which of these options are correct. So first of all, let's find out what f is. So we have this particular integral here. We've been given the equality of these integrals. Integral 0 to x f dash of t minus sine 2t dt is integral x to 0 of f of t tan t dt. So what we are going to use is we are going to make use of the Leibniz theorem, and we're going to differentiate both the left hand side and the right hand side. And upon differentiating that, we are going to get f dash of x minus sine 2x to be equal to f of x into tan x all multiplied by negative 1 because we have to take the derivative of the upper limit and then subtract from it the derivative of the lower limit. The derivative of the lower limit is 1, so 0 minus 1 will become negative 1. So don't miss that minus 1. That's a very key piece of thing in this question, and many students will tend to go wrong in that, because if you get that wrong, the entire question will go wrong. So what do we have here? So we have f dash of x minus sine 2x to be equal to negative f of x tan x. So what I do is I'm going to take the f of x tan x to this left hand side. So I get f dash of x plus f of x tan x to be equal to sine 2x. This is actually a linear differential equation. If you can't see that, substitute f of x with y. So you actually have y dash plus y tan x to be equal to sine 2x. It's a linear differential equation, and we are going to solve this using the method that is there for solving linear differential equations. So we're going to make use of that. First, find out what the integrating factor is. So the integrating factor will be nothing but e power integral of well, whatever is multiplied to y here. So that's tan x. So e power integral tan x dx. Well, integral tan x is log secant x. E power log secant x, well, that's going to be simply secant x. So my integrating factor is secant x. Now we will solve the differential equation. So it's going to be y times the integrating factor, y times secant x, which is equal to the integral of whatever is on the right hand side, sine 2x, multiplied by the integrating factor, which is secant x. So let's simplify this before we actually get into solving, because we can actually simplify this a great deal. Sine 2x is 2 sine x cos x, and secant x is nothing but the reciprocal of cos x. So it's 1 upon cos x. So the reciprocal of cos x will cancel with the cos x in the numerator. So I eventually have just the integral of 2 sine x dx, which is nothing but negative 2 cos x. plus of course the constant of integration, never forget that. So you have y secant x to be equal to negative 2 cos x plus the constant of integration. So I can write this as y divided by cos x to be equal to negative 2 cos x plus the constant of integration. And we've been given that f of 0 is equal to 1. So this means that when x equal to 0, y equal to 1. So using that, we can find out what the constant of integration is. So when x is equal to 0, y is equal to 1 implies 1 divided by cos 0 is 1. That's equal to negative 2 plus the constant of integration, which gives me the value of the constant of integration to be equal to 3. So my f of x or y is nothing but it is going to be c, which is 3 times, and I take the cos to the other side. So it's going to be 3 cos x minus 2 cos square x. So 3 cos x minus 2 cos square x, that's the value of f of x. So now we can look at all the 4 options which are given to us, and we can actually try and find the solutions which are correct to this particular question. The final option, option D, is the simplest to solve because we have to find out the value of f of pi by 3. So we know f of x, so f of pi by 3 is just substituting the value of x with pi by 3. So I get 3 cos pi by 3, cos pi by 3 is a half. So I get 3 by 2 minus 2 times cos square pi by 3, which is going to be 2 times 1/4. So now that's going to be 3 halves minus a half, which is nothing but 2 halves. 2 halves is nothing but 1. So f of pi by 3 is 1. So the option D is actually one of the correct answers. Now option C has an integration. Options A and B have a maxima minima. So if you don't want to attempt these, you can stop here and move ahead because there are marks for partial correct answers. So if you get one option correct, you actually have partial marks. So if you don't want to integrate, you can stop here and move ahead. But of course, we are going to solve the question in entirety. So let's look at option C. That's easier than option D. So option C is nothing but integral from 0 to pi by 2 of y dx, or y is nothing but my f of x. So it's going to be 0 to pi by 2 of f of x dx, which is going to be integral 0 to pi by 2 of 3 cos x. Now I cannot integrate cos square, which is the next term. So I can write 2 cos square x as nothing but cos 2x. In terms of cos 2x, this can be easily written as cos 2x plus 1. So 2 cos square x is nothing but cos 2x plus 1. So it will be 3 cos x minus cos 2x minus 1 dx. So this is very easy to integrate. So upon integration, I will get 3 sine x minus sine 2x divided by 2 minus x, and we have to evaluate this between 0 and pi by 2. Well, when I put the lower limit of 0, everything will vanish because sine 0 is 0, and when x is 0, it's 0. So I just have to be worried about the upper limit. So I have 3 times sine pi by 2, which is going to be 3 times 1 minus sine 2x. Now that is going to be sine pi is 0, so I can easily forget that, and I have the final minus x, which is going to be minus pi by 2. So integral 0 to pi by 2 f of x is nothing but 3 minus pi by 2. So I also get this particular answer as the correct option because option C actually says integral 0 to pi by 2 of f of x is 3 minus pi by 2. So I've got 2 correct answers already. I've got options C and D as the correct answers. Again, if you don't want to proceed, you can stop here because you've already got a few partial marks for this particular question. But of course, we will try and solve this question in entirety. So let's look at the first 2 options, which tell something about f of 0 equal to 1, whether f of 0 equal to 1 is the minimum value of the function or the maximum value of the function is what we are interested in finding out. So maxima, minima, we know f of x. So let's find out what f dash of x is. So you get f dash of x to be equal to negative 3 sine x. Then you have to differentiate this particular expression, which is minus 2 cos square x. So that's going to be minus of 2 into 2 cos x into minus sine x. So if I take out the sine x's to be common out, what I get is a negative 3 plus a 4 cos x. So this expression will be equal to 0 when sine x is 0. So in the domain of 0 to pi by 2, sine x will be 0 when x is equal to 0. And the other thing is when cos x is equal to 3 by 4. Well, we don't know a standard angle for which cos x equal to 3 by 4. So let's just keep it as it is. Anyway, that point of cos x equal to 3 by 4 is not a point of interest. We are interested in finding the point x is equal to 0 because we have to check if f of 0 equal to 1 is a point of a local maxima or local minima. So let's take the second derivative. So f double dash of x, well, this will be nothing but, well, this expression which is negative 3 sine x minus, well, we have 2 into 2 cos x minus sine x. Well, 2 sine x cos x is nothing but sine 2x. So upon differentiating that, I can easily do it and I will get negative 3 cos x. And I have a positive 2 sine 2x there. So I get a positive and I get 4 cos 2x. That's going to be my f double dash of x. So put in the value of x is equal to 0. Well, cos x equal to 0 is 1. So f double dash of 0, that's going to give you a value of negative 3 plus 4, which is equal to 1, and this is greater than 0, which means x is equal to 0 is a point of local minima. So f of 0 equal to 1 is in fact the minimum value of this particular function, not the maximum value. So option B, which says that f of 0 equal to 1 is the minimum value of this function, is the correct answer and not option A. So options B, C and D are all correct answers to this particular question. A pretty lengthy question. There was a little bit of differential equations there, which was with the linear differential equations. Apart from that, this is actually a question that covers a great detail of your calculus. There was integration, there was Leibniz theorem, there was monotonicity. So there was a lot of things that was covered in this question. A very intense question, and I genuinely hope such questions don't come in the exam, because this was actually a pretty lengthy, time consuming question. So in this question, we've been given that dy by dx, that's equal to y multiplied by the derivative of phi of x. So it's y into phi dash of x minus y square divided by phi of x. Now phi of x is a function which satisfies certain conditions. It satisfies the condition that phi of 1 is 1 and phi of 4 is 1296. Further, we know that y of 1 equal to 1. The objective in this question is to find out 1 upon 81 y of 4. It's an integer type of question, so all that divided by 81 and finding out y of 4 and all is just to get a number, a whole number, a complete integer at the end of this exercise. But the actual objective in this question is to find out the expression for the function y. That's the actual objective in this question. So let's try and arrive at the expression for y. So we have dy by dx to be equal to y times phi dash of x minus y square divided by phi of x. So I'm going to divide the RHS into two different terms. So I can write dy by dx to be equal to y times phi dash of x divided by phi of x minus y square divided by phi of x. Well, now I'm going to do something very interesting. I'm going to convert it into a form which will probably be like a linear differential equation. So let's try if that is possible. So what I'll do is I'll divide throughout by y square, and I'll take the first term in the RHS to the left hand side. So what I will actually get is 1 divided by y square multiply, well, that is going to be multiplied by dy by dx. That minus, well, then I have y divided by y square, which is 1 by y, while I have phi dash of x divided by phi of x to be equal to negative 1 divided by phi of x. Well, so far this is what I have. Well, this does not help me because this is not a linear differential equation. That 1 upon y square, which is multiplied to dy by dx, is my biggest problem. So I cannot solve this using the technique of linear differential equation as of now. But there is something else that we can do, and this requires a lot of practice with differential equations. So what I'm going to do is I'm going to multiply throughout by phi of x, and with that minus 1. So I'll multiply throughout by minus phi of x. So what I'll eventually end up getting is I'll get negative phi of x divided by y square dy by dx, plus, because I multiplied by negative phi of x, so I get plus 1 divided by y phi dash of x to be equal to 1. Now look at the left hand side and carefully notice that the second term has 1 by y multiplied by phi dash of x. The first term has negative 1 over y square. 1 by y, when you differentiate with respect to x, you're going to get negative 1 over y square, and then of course dy by dx. So if I were to differentiate 1 by y multiplied by phi of x, then I actually get my left hand side. 1 by y multiplied by phi of x, when you use the product rule and differentiate it, well, you will get negative 1 over y square dy by dx multiplied by phi of x. That's the first term. And the second term will be 1 by y into phi dash of x. So the left hand side is actually nothing but d by dx of 1 by y into phi of x, and this is equal to 1. Well, now I'm going to integrate both sides with respect to x, and what I'll get is I'll get phi of x divided by y to be equal to x plus the constant of integration. A very simple question from here on. That piece of visualization was very important. It'll come after a lot of practice of differentiation and differential equations. If you are not well equipped with differential equations, and if you do not see the pattern of differentiation, well, these things will not come into your head. So a lot of practice is very important to get that piece of visualization as soon as you look at the question. That's the key bit in this particular question. After that, it's very trivial now, because now in order to find the constant of integration, we're going to make use of all the information given to us. We've been given that phi of 1 is 1 and y of 1 is 1. So when x is 1, y is 1, and phi is also equal to 1. So we're going to plug in that. So I get 1 divided by 1 to be equal to 1 plus the constant of integration, which immediately gives me the constant of integration to be equal to 0. So what I get is phi of x is equal to xy. But to be honest, we don't want the expression for phi of x, we want the expression for y. So I get y to be equal to phi of x divided by x. Now I need to find out what the value of y of 4 is. In fact, I need to find out 1 divided by 81 y of 4. Well, that's nothing but 1 divided by 81, phi of 4 divided by 4. Well, phi is a function which gives a value of phi of 4 to be equal to 1296. So I have 1 divided by 81 into 1296 divided by 4. Well, 4 ones are in 4, 324 times in 1296. 81 ones are 81, 4s are 324. So the correct answer to this integer type of question is 4. A rather beautiful question, but it really requires you to have an eye for patterns in differential equations. Without that, it's pretty difficult to solve this question. So you've already seen the importance of patterns and the ability to notice them in differential equations questions. So we're going to look at one more question, which is going to explore this ability of yours to identify patterns in differential equation questions. So here's the question. We've been told that x cube dx plus yx square dy divided by under root of x square plus y square is y dx minus x dy. The other piece of information is y of 1 is 1, and you know why this piece of information is given. This piece of information is only given to find out the constant of integration. So we're going to look at that piece of information right in the end and focus on the differential equation in hand. So it looks like a pretty difficult differential equation first up. So let's try and identify patterns here. The first thing I'm going to do is there is an x square common in the numerator. I'm going to take them out. So I'm going to take an x square common out. So I get x dx plus y dy divided by, of course, the under root of x square plus y square. That stays, and this is equal to y dx minus x dy. Now look at the left hand side. You have an under root x square plus y square there. Now what will happen if you differentiate x square plus y square? If you differentiate x square plus y square, you are going to get 2x dx plus 2y dy. So the differential of x square plus y square is nothing but 2 times x dx plus y dy. Well, look at the numerator. You have an x dx plus y dy there. Brilliant. Now let's go one step further into identifying the pattern. What will happen if you differentiate under root of x square plus y square? Well, the differential of the under root of x square plus y square is 1 divided by 2 times under root of x square plus y square and the chain rule. So that's going to give you a 2 times x dx plus y dy. The 2's are going to cancel out and you actually get the entire left hand side without the x square. So this pattern we identified because x dx plus y dy is the differential of x square plus y square divided by 2. So that's how you identified this pattern. So the left hand side is in fact nothing but x square multiplied by the differential of under root of x square plus y square. So I don't like that x square there, so I'm going to bring it on to the right hand side. So what I have is the differential of under root of x square plus y square. Well, that is going to be equal to, divide throughout by x square. So what you have is y by x square dx. And then you have negative of 1 over x dy. Correct? So now look at the pattern on the right hand side. Well, you have y over x square dx and negative of 1 over x dy. When you differentiate 1 over x, you're going to get negative 1 over x square. So if you differentiate negative 1 over x, you are going to get 1 over x square dx. So isn't this nothing but the derivative of negative 1 over x into y? So when you differentiate the first term, you're going to get negative 1 over x. The differential of that is 1 over x square dx and then y as it is. And then the second term, when it's getting differentiated, you'll have negative 1 over x as it is and dy. So again, you look at the pattern and this pattern emerged out of the product rule of differentiation. The left hand side pattern emerged out of the chain rule. The right hand side pattern emerged out of the product rule. So you have to remember this, that visualizing patterns, that will come only with a lot of practice. So do a lot of practice in order to be able to visualize these things. Because from here on, the question is very, very straightforward. You're just going to integrate on both the sides. And what you're going to get is under root of x square plus y square is nothing but negative y over x plus the constant of integration. And you need to find out the constant of integration. Please don't commit a mistake here because you've done all the hard work. Going wrong here would be actually tragic. We've been told y of 1 is 1. So plug in the value of x equal to 1, y equal to 1. So what are you going to get? You get under root of 2 to be equal to negative 1 plus the constant of integration, or c is actually equal to 1 plus root 2. Well, that was very trivial. So the solution to the differential equation which was given is nothing but under root of x square plus y square is nothing but negative y over x plus 1 plus root 2 or root 2 plus 1. So this is the solution to the differential equation which was given to us. Again, a lot of emphasis on identifying patterns in differential equations. Again, in this question, the patterns were based on the chain rule and the product rule. Beautiful question. And in order to solve such questions, you actually have to practice a lot. Now, this is a multiple correct answer type of question. And again, you're going to make use of patterns here. So what has been given to us? We've been given a differential equation. Dy by dx is equal to x square plus y square plus 1 divided by 2xy. And of course, the condition to find out the constant of integration, which is y of 1, is 1. Now, why do I say that we need patterns here? Because if you look at this expression, of course, separating the variables, that's impossible here. So that is completely off the table. Homogeneous, that +1 in the numerator of the right hand side is going to make this not a homogeneous differential equation, and you cannot even make it a linear differential equation because it's going to be very difficult for you to write it in the form of a linear differential equation. So then the only resolve that we have to solve this question is make use of patterns. Let's try and identify patterns once more, because that seems to be the trend these days in the questions which come from differential equations. You need to be aware of pattern identification. So what I'm going to do is I'm going to cross multiply everything, and let's not have any ratios on either side of the left hand side and the right hand side. So what I get is I get 2xy dy to be equal to x square dx plus y square dx plus dx. Okay, now let's look at the left hand side. I'm going to rewrite my left hand side as x times 2y dy. So x times 2y dy, that's equal to x square dx plus y square dx plus dx. Okay, so now in the left hand side you have 2y dy. When do you get 2y dy? If you differentiate y square, you're going to get 2y dy, and there is a y square in the right hand side, so I'm going to bring everything with the y square dx to the left hand side. So what I'm going to get is I'm going to get x times 2y dy minus y square times dx to be equal to, well, right hand side everything is in terms of x's, so there's almost a variable separation there, so I'm going to keep it as x square plus 1 times dx. That's a variable separated thing, so it's going to be very easy to integrate the right hand side, so let's keep it that way. Now we can't make use of the product rule because of this rogue negative. If not for that negative, if it was a positive, we could have straight away made use of the product rule. We had x times the derivative of y square, and we had y square times the derivative of x. That would have been perfect for product rule, but for that negative. So this is bad news for us. So we have x times the derivative of y square minus y square the derivative of x. So we have the second term, which is x, multiplied by the derivative of the first term, y square, minus we have the first term, which is y square, multiplied by the derivative of the second term, which is x. So this reminds me of the quotient rule, because in the quotient rule also we have the second term multiplied by the derivative of the first minus the first term multiplied by the derivative of the second. So what I'm going to do is I'm going to divide this expression on the left hand side by x square, because my second term was x. So I'm going to divide by x square, because then I'll have the second term square in the denominator. So then what I have is I have x multiplied by 2y dy minus y square multiplied by dx divided by x square, and I'll have to divide by x square on the right hand side also to maintain my equality. So what I get is I get 1 plus 1 upon x square dx. Now my left hand side is a pattern, and what I actually have on the left hand side is simply nothing but the derivative of the first term divided by the second term, y square divided by x. The derivative of y square divided by x is actually equal to 1 plus 1 upon x square dx. Well, the right hand side is a variable separated, so that's very easy to integrate. So now we're going to integrate both the sides. So upon integrating, what we get is y square upon x is equal to, well, integrating 1 plus 1 by x square dx is going to give me an x minus 1 upon x. And of course we need the constant of integration. Well, a very beautifully crafted question. Well, we have seen in the previous questions patterns related to chain rule and product rule, and in this question we have seen a pattern related to the quotient rule. So beautifully crafted question. Now we are going to see what is the value of this constant of integration, because we've been given the condition y of 1 is 1, so we're going to plug in x equal to 1, y equal to 1, and we get 1 equal to 1 minus 1 plus the constant of integration, which gives me c to be equal to 1. So my differential equation, the solution to that is nothing but y square upon x is equal to x minus 1 upon x plus 1. Well, we could have left this in this particular state if it was the board examination, but unfortunately this is a multiple correct answer type of question, so we have to match this with one of the options given. So let's do a little bit of manipulation. So what I'm going to write it as is y square upon x is equal to x square minus 1 plus x, all divided by x. The x's from the denominators are going to cancel out, so what I have is y square to be equal to, well, again, x square minus 1 plus x is not one of the options, so I'm going to take the x common out. I get x plus 1 and then minus 1. Now this is one of the options. Y square is equal to x times 1 plus x minus 1 is an option. So option C, which says this is a solution of the differential equation given to us, is a correct answer to this question. You can as well stop here because there are marks for each correct answer, so you will get partial marks, but of course we aim to get all the marks, so we are going to try and solve option A and B. We are going to see if this represents a circle or if it represents a hyperbola. Well, it is not a circle for sure because it's going to be nothing but x square minus y square plus x minus 1 equal to 0. This cannot be a circle because the coefficient of x square and y square are different. But that does not guarantee that it is a hyperbola. This is an advanced examination, so maybe they have tricked you by giving two options, neither of which are correct. So you can't definitely say that this is a hyperbola. For all you know, it can be any of the second degree curves. It might as well be a pair of straight lines. You never know what is this curve. So let's try and solve this. This actually looks like a hyperbola, might be a hyperbola. So if you use completing the square, you can write it as x square plus 2 times 1 half times x. Well, then you have 1 half whole square minus 1 half the whole square minus y square minus 1 is equal to 0. Well, this is actually a hyperbola straight away because you have x plus a half the whole square minus y square to be equal to, well, you don't even have to solve the right hand side. It's going to be 1 plus a half the whole square, 1/4, which is actually 5/4. So this is actually a hyperbola. So it is a shifted hyperbola which has its center at negative half comma 0. So option A, which says that the differential equation, the solution to the differential equation is actually a hyperbola, is also a correct answer to this question. So options A and C are the correct answers to this question. Again, patterns had to be identified. So these days in differential equations, we do not see a lot of questions that directly test your understanding of homogeneous or linear differential equations. They will always make the question slightly tricky by asking you to identify patterns and solve it in this particular way that we have shown in the last 3 questions. If it's a direct question like the first question was a linear differential equation question, it turned out to be a very long question because lots of concepts were involved there. You had concepts from differential equations, from integration, and from application of derivatives. Too many concepts will be covered in such questions. I will always prefer the second type of question, which is questions which involve pattern finding, even though they are more difficult than the first one, because these questions become really interesting if you know how to solve them. So practice these questions in abundance so that these things get embedded in your system, and then you enjoy solving these questions in the examination. So that was differential equations for you. Again, an important chapter from calculus. Of course, not as important as definite integrals is, but this chapter is also a very vital and important chapter for your advanced examination. I hope you had fun in this particular video. If you actually liked the video, please subscribe to our channel in case you've already not done that. Press on the bell icon, because every time we make such videos, you will be notified about them, and you will be actually able to enjoy these videos which are about different chapters from the JEE Advanced examination point of view. So I sign off today, and I will hopefully be back again with yet another chapter. Till then, prepare well for your examination, and hopefully we'll see you again with yet another chapter.
For more videos and live lectures on the JEE, Click on the subscribe button now.